We're going to start Module 8 with a discussion of buffer systems. This is a deeper dive into equilibrium topics, and we've already spent a lot of time talking about acids and bases in Module 7. And so you understand already that weak acids and weak bases do not completely dissociate, and so they do set up an equilibrium. And this equilibrium that is set up is crucial in forming buffer systems, which our creator has used all over creation to keep certain things within a certain pH level, because that's what supports life. Your author specifically mentions that our blood is a buffered system because it's able to keep our bodies within a very narrow pH range. And if we get outside of that range, we get very, very sick very, very quickly. Experiment 8.1 showed you a buffer solution, and it showed you how they are affected by the addition of an acid. I want to delve a little bit more deeply into that and try to explain to you why that is the case. This is one of those times that I wish I actually had an actual lab that I could show you, and I wish that I had a pH meter that I could actually drip the acid into these different solutions and show it to you. I can't do that, so we'll have to do it this way. But what I want you to imagine is that I have a liter of just plain old distilled water, which means there's no other minerals in it, it's just pure water. And so if you have only water, the pH of that is going to be at 7.0. Over here, I also have a liter of seawater. And seawater, as you probably are all aware, seawater is very salty, but it also has a lot of other different types of minerals in it. And it also has carbon dioxide dissolved in it. And so this has a pH of 8.2, so it's just slightly on the basic side. Now, what would happen if I added just 1/10 of a milliliter? I mean, that's just a few drops of some 1 molar hydrochloric acid to each one of these containers. Now, let's talk about exactly how much that is. That's 0.0001 liters. And if you remember, the units for molarity are moles per liter. So if I multiply volume times molarity, that's going to give me number of moles. So I'm adding 0.0001 moles of hydrogen ion, because hydrochloric acid is a strong acid. It's going to dissociate completely. I'm adding just this number of moles to this liter of distilled water. So what does that mean? Well, if I have 0.0001 moles of hydrogen ion, that means that my hydrogen ion concentration is going to be 0.0001 molar, because this is within a liter of water, okay? And we already also know that pH is the negative log of the hydrogen ion. So if I take the negative log of this, that is going to give me a pH of 4. So my new pH, if I add just that tiny amount of hydrochloric acid, is going to drop my pH all the way to 4. Now, what happens if I add it to seawater? Now, we do have to keep in mind that seawater is going to vary from one location to another. This is going to be a generalization, but in general, if I add the same amount of hydrochloric acid to the same volume of water, but this time it's seawater, my pH is only going to drop to 7.6. Why is that the case? Okay. Well, first of all, seawater has a great deal of carbon dioxide dissolved in it. So if I take H2O and I dissolve carbon dioxide gas in it, it's going to set up an equilibrium where it makes carbonic acid. Now, carbonic acid is a weak acid, and so again, as you're already aware, carbonic acid is going to partially dissociate into a hydrogen ion and a bicarbonate ion, okay? So what happens when I add the hydrogen ions from here? Well, if you remember Le Chatelier's principle from your first year course, you remember that if you have a a reversible reaction with an equilibrium setup, if you add something to one side, it's going to shove the equilibrium back to the other side because it's going to try to undo whatever change you made. So if I add in hydrogen ion, this equilibrium is going to be shoved back this direction to get rid of that extra hydrogen ion and turn it back into carbonic acid again. And so the equilibrium will shift back to the left, and what will happen then is that will not have an appreciable effect on the level of hydrogen ion. Now, I say not an appreciable effect. It does affect it because, as you can see, it did still drop it, but it didn't make nearly the drastic effect that it had over here. And so when I add that hydrogen ion, this equilibrium gets disturbed because the hydrogen ion is then going to go back this direction and try to shove off this equilibrium back to the other side. As a point of reference, what would happen if I added base to seawater? What's going to happen to the pH there? Well, again, because this is a buffer, it is going to react in such a way because it is very resistant to change. Both hydrogen ions, or both, let me rephrase that. The carbonic acid is a stronger acid than water is. And the bicarbonate ion is a stronger base than water is. So why am I referring to water as an acid and base? Well, if you recall, we've seen that water can act as either an acid or a base. It's amphoteric. It can act as either one depending on what you put it in the presence of. So in this particular case, the carbonic acid is a stronger acid than the water is. So if you put base in it, the base is going to react with this and it's going to shove it back this direction. If I add acid, it's going to have hydrogen ions in it and it's going to react and it's going to go back this direction. So what this is basically doing is it's preventing those hydrogen ions and hydroxide ions from reacting with the water that's present because it's providing something else for them to react with, and it buffers against a reaction with water. It buffers against a change in pH, and so that's why it's called a buffer system. Okay, so what happens in a buffer system is that because you have an acid and its conjugate base, both of which are stronger acids and bases than water is, they provide other acids and bases to react with so that you're not going to react directly with the hydrogen and hydroxide ions in the water, and therefore your hydrogen ion concentration is not appreciably affected. Again, I said not appreciably. We'll learn how to calculate just how much it's affected in the upcoming module or in the upcoming sections. But I did want you to understand that it's basically what we're doing is we're protecting that water from having a reaction with the acid or the base that you add. I do want to make one other point, and that's that you have to have a weak acid with its conjugate base. You can't just take any acid and any base, or you're just going to have an acid-base reaction. You have to have an acid-base conjugate pair. You could also take a weak base and its conjugate acid to form a buffer system as well. So again, not just any acid and base, but you have to have a weak acid with its conjugate base or a weak base with its conjugate acid in order to make a buffer.